Okay, this is the first part of lesson 4.4, and there's a few things that we need to review from Algebra 1, basically, before we start in on the lesson. And it's very easy things. Um, One would be how to find something like this. Let's say it's 4 to the 3 halves. And we want to do this without our calculator. Okay, here's how I always think about it. I always look at my bottom number first. Okay, the 2 means take the square root of 4. If it were this, let's say to the 2/3, my bottom number is a 3. That means take the cubed root of 8. Okay, so if I take the square root of 4, that's 2, and then I need to cube it. So 2 cubed is 8. Okay, if I have another one like this, the 3 means take the cubed root of 8. Well, the cubed root of 8 is 2, and then I need to take that answer and square it. So that's 4. So let's do another one. Let's do 16 to the, I don't know, 3 halves. So the 2 means take the square root of 16, which is 4, and 4 cubed. So that means 4 times 4 times 4. 4 times 4 is 16. 16 times 4, what is that, 64? So that's one thing that, just a little reminder of how to find those without using your calculator. Okay, so if you look at your notes, the very first thing on your notes talks about the fundamental theorem of calculus. So this is a theorem that they give us. And there's two parts to the fundamental theorem of calculus. I'm going to call this part 1. In your books, they'll label them different. This might be part 2 in a different book, but it really doesn't matter what the label is. We just know that this is part of the fundamental theorem of calculus. Now, if you hear a name like the fundamental theorem of calculus, I would say that that's a pretty important theorem if it's called the fundamental theorem of calculus. That just makes sense. And here's what it says. If f is continuous at every point of this closed interval AB, and if capital F, remember that's the symbol we said we're going to use for antiderivative. So if f is any antiderivative of that closed interval from a to b, then the integral from a to b of f of x equals, I'm going to take the integral and then substitute in my b minus the integral and substitute in my a. So it's actually very easy and you pretty much already know how to do it. We just have numbers now to plug in. Before, we had indefinite integrals. Remember what an indefinite integral is? It has no numbers here. So you already know how to find indefinite integrals, and then we put plus c. You actually know how to find a definite integral, for example, 0 to 2 of x dx. We did this in a previous lesson by graphing this. I'm going from 0 to 2. That would be 0. That would be 1. Here's the graph of that. And we found the area under that curve by finding the area of that triangle. They were nice, neat geometric shapes. So if I was going to go ahead and do this, area of that would be 1/2 my base, which is 2, times my height, which is 2. So when I simplify that, my area is 2. Okay? So I know this part isn't on your paper, but now I'm going to show you how to use the fundamental theorem of calculus to do this exact same problem. So on the back of your worksheet, I want you to write this down. All right, we're going to use the same problem. 0 to 2 of x dx. Okay, so the first thing we're going to do is we're going to find the antiderivative, just like we have been. So I add 1 to the exponent, divide by my new exponent. So I have x squared divided by 2. And normally we would put plus c, but since this is a definite integral, I'm not going to put the plus c. I'm going to be substituting these numbers in. Now here's how I write the notation for that. After I find the antiderivative, I put this vertical line, and then I'm going to put my upper and lower limits. Now, if you'll see what this says, it says find the antiderivative and then plug your top number in. So that's what I'm going to do. We found the antiderivative. I'm going to plug my top number in, so 2 squared over 2 minus whatever I get when I plug in my lower limit, 0 squared over 2. And that's it. You find the antiderivative, plug your upper limit in minus your lower limit. And then I'm going to simplify that. 4 over 2 minus 0, which is 2. So either way that we did this problem, we got the same answer. Now here's the deal. Sometimes it's not nice, neat geometric figures that we know how to find the area of. Okay? It could be a parabola, something that looked like this. Then I have to find the area. Okay? We found the area before by using LRAM and RRAM and MRAM and to get an approximation. Now we need to be able to find the exact area. So this is where this theorem comes into play. So let's do example 1. You might write small because I didn't leave a lot of room for you. So example 1, x squared minus 3, and I'm going from 1 to 2. If I did graph this, this would be a parabola shifted down 3 units from 1 to 2, so it's not going to be a nice, neat geometric shape. So let's find the antiderivative. This is going to be x to the third over 3, because I add 1 to the exponent, divide by my new exponent, minus the antiderivative of 3 is 3x. And I'm evaluating by plugging in my 2 and my 1. You always plug in your top number first, or my upper limit. So I have 2 cubed over 3 minus 3 times 2. I plugged in my top one in place of all of your x's. Minus, now you have to be careful because it's minus everything that comes next. So I put parentheses or brackets so I don't mess up on my signs. Now I'm going to plug in my lower limit. 1 cubed over 3 minus 3 times 1. So we're going to do all this without our calculator. So 8 thirds minus 6, I'm going to distribute my negative, minus 1 third plus 3. Now let's do this. I'm going to get a common denominator. 8 thirds, my common denominator is going to be 3. So 6, that's going to be 18 on top, because 18 over 3 is 6, minus 1 third plus 9 over 3. So 8 minus 18 is negative 10, negative 11 plus 9, negative 2 thirds is my area. And that kind of makes sense because if I think about it, just to give you a quick sketch, this is that, and I'm going from 1 to 2. So doesn't it make sense that my area is negative because it's going to be below the x-axis? All right, so example 2. First thing I need to do is rewrite my problem. Okay, first thing I need to do is rewrite my integral. So I'm going to go from 1 to 4. This is 3x to the 1/2 dx. Okay, so we already know this is a constant. So remember we always brought our constant out in front. So I have 3 from 1 to 4, x to the 1/2 dx. So now we're ready to find the antiderivative. So I'm going to bring it down here. 3 times, add 1 to the exponent. So 1/2 plus 2/2 would give me 3/2. Normally I would divide by 3/2, but I don't want to divide by a fraction, so I'm going to multiply by its reciprocal, 2 thirds. And I'm evaluating from 1 to 4. So do you see what happens to my 3's? These are going to cancel. So really, I have 2x to the 3/2 from 1 to 4. So now we're ready to plug in our numbers. 2 times 4 to the 3/2 minus 2 times 1 to the 3/2. So this is why we practiced that first part. So we always have to do our exponents first. So 2 4 to the 3 halves. So the square root of 4 is 2, and 2 cubed is 8. This, anything 1 to any power is just 1. So that's going to be minus 2. So 16 minus 2, 14. Example 3. So I'm evaluating or finding the area of the curve from 0 to pi over 4 of secant squared x. Good thing is secant squared x is one of those easy antiderivatives that's on your chart or on your notes. The antiderivative of secant squared x is tangent x from 0 to pi over 4. So now I'm going to plug in my upper limit, tangent of pi over 4 minus the tangent of 0. So the tangent of pi over 4 is 1. Tangent of 0 is 0. So my answer is 1. Example 4. Okay, example 4 is different, and the reason it's different is because it has absolute value. So let's look and see what this graph would look like. We know absolute value is just a v. Okay, it's going to be shifted to the right 1/2. It's always this divided by this. So if this is 1, this is 2. Here's what that graph looks like. Okay, and look what they're wanting. They're wanting from 0 to 2. So I need to write, they're wanting this right here, and this would go on this area. So it actually forms two triangles, but we're going to do it using the fundamental theorem of calculus. When you have absolute value, you have to break it up into two separate integrals. I'm going to rewrite this. This is 1, 2. I have to write an equation for this line and write an equation for this line. So here's my first one. From here to here is 0 to 1/2. So I'm going from 0 to 1/2. And this equation is 2x minus 1, but it's negative because my slope is negative. Do you see that the slope of that is negative? So it's negative 2x minus 1 plus the rest of this. The rest of this is that equation, but I'm going from 1/2 to 2. So 1/2 to 2 of 2x minus 1 dx. So now, before I do this, I need to distribute my negative. So I have from 0 to 1/2 of negative 2x plus 1 dx plus 1/2 to 2 of 2x minus 1 dx. I'm going to use a different color here. Okay, so let's find the antiderivative. Negative 2x squared over 2 plus x from 0 to 1/2. Do you see here that my 2's are going to cancel? So now I really just have negative x squared. So I'm going to plug in my numbers. Negative 1/2 squared plus 1/2. So I did my 1/2. Minus, now I'm going to plug in 0. 0 squared plus 0. So I have my negative out in front. 1/2 squared means 1/2 times 1/2, which is 1/4, plus 1/2 minus 0. And negative 1/4 plus 1/2 means negative 1/4 plus 2/4. So my answer is 1/4. I'm looking because that's not supposed to be my answer. Let's see here. Negative 2x plus 1. Let me see if I can find my mistake real quick. Negative 1/4 plus 1/2. Oh, okay. Yeah, I'm good for that one. There's my 1/4 for this one. Now I need to do it for this one and add the two answers together. I just wasn't finished. So I'm going to do that in a different color. Okay, so here, right here, I'm going to find the antiderivative. 2x squared over 2 minus x from 1/2 to 2. Again, my 2's cancel, and now I'm going to plug my numbers in. 2 squared minus 2 minus 1/2 squared minus 1/2. So I have 4 minus 2, 1/4 minus 1/2, 2 minus 1/4 minus 1/2. Of course, my phone is ringing. 1/4 minus 2/4, negative 1/4. So that's 2 plus 1/4, so 2 1/4. So I have 2 1/4 plus 1/4, that means 2 1/2. Because I'm adding these two things together. And that's your answer. All right, last one. Find the area of the region bounded by the graph of the x-axis and the vertical lines x equals 0 and x equals 2. Sketch the graph and set up the integral to solve. So I don't have my calculator on here, but if we graph this, 2x squared minus 3x plus 2, and I'm just going from 0 to 2. Okay, this is going to look something like this. So here's 1, here's 2. Okay, something like that. Okay, and I didn't realize you're going to have to graph this. I didn't look that far ahead. So it looks something like that. Okay, now let's set up our integral. I know I'm going to go from 0 to 2 of this graph, 2x squared minus 3x plus 2 dx. So now we're going to find the antiderivative. 2x cubed over 3 minus 3x squared over 2 plus 2x from 0 to 2. I'm going to plug my 2 in. 2 cubed over 3 minus 3 times 2 squared over 2 plus 2 times 2 minus whatever I get when I plug 0 in. Do you see that I'm going to get 0 for each one of them? So now we're going to simplify. 2 times 8 over 3 minus 3 times 4 over 2 plus 4. So this is 16 over 3 minus 12 over 2 is 6 plus 4. If I find a common denominator, 16 over 3 minus 18 over 3 plus 12 over 3, 10 over 3. That's the area under that curve. Okay, that's the end of part 1 for section 4.4.